Hello everybody, this is the notes for section 2.1, geometry. We're going to kind of shift gears a little bit. We are going to be talking about geometric stuff, but it's going to look more wordy. We're going to be dealing with a lot of sentences and definitions and the way you write them, and less numbers, more words. Okay, so a couple of definitions and terms to be familiar with. A conjecture, unproven statement that is based on observations. Basically, it's an educated guess. All right, to come up with that educated guess, you use what's called inductive reasoning. You're looking at a pattern, you see a pattern, there's no way to prove it, but you're just extending that pattern out, making a conjecture for the general case. It's just a way to think. Okay, you're not using any specific numbers or anything. You're just thinking, all right, this appears to be the pattern, and say, I think this is what it is. And a term called counterexample. When you have a conjecture, if it's false, all you need to do is just come up with one counterexample. It's just that it's an example that says this conjecture is not correct, and here's a case where it's not correct. Okay, so essentially with this section, we're just kind of looking at patterns for the most part. So we have a visual pattern here. So hit pause, take a second, try to draw the next figure in this pattern. Okay, so you can see the pictures are kind of the same. We have the the squares. Inside them are smaller squares. But it just seems to be that they are rotating. So the next one should just be a square. There's your four smaller ones. The key thing to notice is that small square with the 4, it started in the upper right, now it's in the upper left, lower left, now it should be in the lower right. And we have 2 of them that were shaded. I'm just kind of following this one around. Lower right, upper left. Now that should be in the lower left. And this one's kitty corner from that. Across from the squares here, we have this. So, just coming up with a pattern. All right, now dealing with numbers, come up with a number pattern. All right, we're looking at this, we're saying, okay, I think this is what it is. We're just going to use inductive reasoning to make a conjecture. Here's what I think the pattern is going to be. So, it says describe the pattern in the numbers below and write the next 3 terms. So, it's just a matter of just trying out things. I look at this, okay, I see I'm adding 6. Now I'm adding 24. Now I'm adding 96. Okay, there does not seem to be a pattern with those. You just try something until you start figuring things out, seeing the numbers. All right, I see 2 to 8. Well, maybe if I multiply by 4. All right, 8 to 32. Well, multiply by 4 again. Let's just see if that works. It looks like this is going to be the pattern, but you keep on trying. 32 times 4 is indeed 128. There's our pattern. So, the next 3 terms, 128 times 4, just getting the calculator out, 512. Next term should be times 4, 2,048. One more time for the next 3 terms, 8,192. Okay, so there's the pattern for that list of numbers, and we just continued it on. All right, for this second example here, it looks like, again, just you try stuff. Adding 3, adding 6, adding 12. Well, kind of a pattern there. The difference between these, plus 3 plus 6, well, that's a difference of 3. Between 6 and 12, it's a difference of 6. Well, just kind of repeating that. So, the don't really like that pattern. Not really sure. It could go in a couple different directions. It's not really what we want. So just looking at the numbers, thinking my way through this, I notice that each of the next terms is a little bit more than twice the previous term. 2 times 2 is 4. Add 1. There's my 5. All right, let's see if that works. 5 times 2, or twice of 5, is 10, plus 1. There's my 11. All right, 11, twice of 11 is 22, and then I add 1. Okay, there's my 23. This is the pattern. So you're taking the previous term, multiplying it by 2, and then adding 1 more. So to continue this pattern on, 23 times 2, 46, plus 1, 47. Get my calculator again. I'm going to double that term. 47 times 2 is 94. Add 1. 95. Double that. 181, 90, plus 1, 191. Okay, I'm going to let you try that last one. We'll talk about it in class. So, make and test a conjecture. So basically, you're given a statement. Make and test a conjecture about the product of any two even integers. To make a conjecture, all you're doing is looking at a pattern. So let's just start looking at some things. Product of any two even integers. 2 times 4, we get 8. 4 times 6, we get 24. 10 times 12, we get 120. So the question is, make and test a conjecture about the product of any two even integers. What do we notice about those numbers? If we want some more, 8 times 10 is 80. Okay. All these numbers seem to be even. So, our conjecture, the product of any two even integers is even. We didn't get an odd answer, and I don't think we're going to. So you could try to come up with a counterexample, but you're not going to with this. This is the conjecture. Okay. The next one, the average of any two consecutive odd whole numbers is. Okay, so we've got a couple of things here. The average of any two consecutive odd whole numbers. Whole numbers are like your counting numbers, 1, 2, 3, 4, 5. So they got to be odd, they got to be consecutive. So the average of them also. So we're adding up and dividing by 2. Consecutive odd whole numbers, 1 and 3. They are consecutive odd whole numbers. The average of those is 2. 3 plus 5. That's 8 divided by 2. We got an average of 4. Okay, so we're looking at these numbers. Consecutive odd integers. So 11 plus 13. Those are consecutive odd integers. The average of those, that's 24 divided by 2. That's 12. What seems to be happening with our answers? They all seem to be even. Okay, to find a counterexample, again, if you have a conjecture and you're trying to prove it's false, or trying to show it's false, you just need that one counterexample. The whole idea of a conjecture is, if it's true, it's going to be true for all numbers, all cases. So if you can come up with that one that is not true, that's all you need. All right, find a counterexample. The square root of a number x is always less than x. So, square root of 4, that is 2. Well, if x is 4, is 2 less than 4? Not so much, okay? So that's not really a counterexample. It kind of just shows that this thing is correct. Square root of 16 is 4. If x is 16, 16 is, well, hang on, the square root of a number x is always less than x. Yeah, this is true. We got the square root 4, it is less than 16. Okay, so it's just showing that. So we looked at some normal numbers. What if we go the other direction? Can you take the square root of a negative number? I hope all of you are saying no in your head. So let's look at fractions. Square root of 1/4. You take the square root of a fraction, you take the square root of the top, and the square root of the bottom is, okay, so the square root of a number x, so in this case, x is 1/4, is 1/2 less than x. Not so much. There's our counterexample. We came up with a number x that the square root of it is not less than the number. For the next one, the difference of two positive numbers is always positive. So difference means subtraction. The difference of two positive numbers is always positive. We're trying to come up with something where we're not going to get something that is always positive. So like 3 is a positive number. Minus 6, that's a positive number. We get -3. That's not positive. There's our counterexample. Okay. That's it for today. Have a good night. See you tomorrow.